In this lecture, we will prove two theorems. First is the range space is a subspace of W and null space is a subspace of PF. Okay, so first we will prove that range space is a subspace of W. So let T such that V to W where field is same have a linear transformation. Be a linear transformation. Then what will be the range space? The range space is the collection of all the element in W which is image of some element of V. Okay, if we take X from V, then image of X will be in range of T. This is the subset of W. Okay, now we will show that it is a vector space. Then it will be the subspace. Okay, to show it is a subspace of W. So firstly, we will show the range space of T is non-empty. Means we have to show there is an element which always lie in range space. Okay, so since V is a vector space, okay, we have given that T is a linear transformation from V to W. So V and W will be both vector space. So V plus will be a group or abelian group, we can say. Okay, abelian group, because we have defined vector space. V should be abelian group with respect to plus. Okay, we have defined, you can check out my video. Okay, so identity element will be in V since it is a group, or a group always contains identity element with respect to operation. So it should have identity element with respect to plus, because V is abelian group with respect to plus operation. So we know 0 is the identity element with respect to plus. Okay, so this will belong into V. So what we have proved in previous lecture, that T of 0 equal to 0. So this 0 belongs to V and this 0 belongs to W. Okay, and what is the definition of range space? Range space of the is the definition as definition that any element will be in the range space if that element is the image of some element in the V. So it is the image, so it will be in the range space. Means range space is non-empty. Okay, now we proceed further. Assume we have two elements. As range space is non-empty, we can have an element. So we have two elements, x and y belongs to range space. And assume alpha comma beta is a constant taken from the field type. What we know, that the field should be same in the linear transformation. The field of the domain vector space and codomain vector space should be same. So we have taken two elements, alpha beta belongs to field and x y belongs to range space. And we have to show range space is a subspace of W. So what we need to show, alpha x plus beta y belongs to range space. Okay, the test, how to test any subset will be the subspace or not. I have given a video on this topic. You can visit that video. Okay, if you don't visit it till now. So alpha x plus beta y belong into range space, we have to show. So now as x belong into range space, what does mean by x belonging to range space? Means that there is an element in V such that their image will be x, because range set is the image set. Okay, so we have a V1 from V such that their image is x, and V2 from V, capital V, such that T of V2 is y. Okay, now this is the definition of image, because we have a functions, and function always has image, always should have. There is an element, maybe there can be another element v3 such that t of v3 equal to x, but at least one v1 will be in v vector space such that t of v1 is x and t of v2 is y. Okay, so now assume v equal to alpha v1 plus beta v2. Since this element is in v1, so this element in capital V vector space, v2 is also in vector space V, so their linear combination will also be in V. So it means V is in V. Now, if you find the image of this element, what will be? Since T is a linear transformation, alpha will be come out T of B1. And because of linearity, it will be alpha T of B1 plus beta T of B2. This is because of linearity. Now what we know, T of B1 is X. Okay. We know that T of B1 is X and T of B2 is Y. So T of B1 is X, T of B2 is Y here. Okay. So this is alpha X plus beta Y. It means this element is in W and it has pre-image V. So it will be in the range space. All those elements will be in range space, which is the pre-image of some element of V. It means it will be in the range space as V belongs to V. So we have shown that range space is actually a subspace of W. Okay. Similarly, we will show that null space is a subspace of V. So we have a linear transformation T of VF to WF. Now think about that null space is all element of V such that T of X is zero vector, means all element in V. If this is a V, this is a W, then all those elements we will choose such that their images will be zero vector. Okay, all elements should have zero vector. So it is a subset of V. So it is non-empty because zero vector always has image 0. We have proved. So it is non-empty. So we can take two elements. So we have taken two elements x and y, which is in the null space. What does it mean? T of x equal to 0. By the definition, any element will be in the null space if their images is 0 and T of y equal to 0. Okay, so now we have to show alpha x plus beta y is in the null space. Okay, to show this is a subspace, what we show? What we need to show that alpha x plus beta y will be also in null space. Okay, so what we know, T alpha x plus beta y will be alpha T of x plus beta T of y because of linearity. Tx plus y is equal to T of x plus T of y, and T of alpha x equal to alpha T of x. This is the definition of linear transformation. That is what we have used here. Now we know T of x equal to 0 vector. So here we have written 0 vector, and T of y equal to 0 vector. So we have written here 0 vector. Now if you multiply this vector and add, we will get 0 vector only. This means that alpha x plus beta y is in the null space because their image is 0 vector. Okay, hence say null space is a subspace of V. Okay, thank you for watching.